Let's talk about Rolle's theorem, which is a special case of the mean value theorem. But usually it's good to introduce and understand Rolle's theorem first, because if you can get a good feel for how that works, then the mean value theorem essentially follows from that. So let's do it in pictures first. So imagine we have a function and it's a continuous function, at least on a certain interval, and let's go up like so. And what we're interested in is this interval here between a and let's be real careful here. So a goes up to about here, and then we'll have b come down like so. B. Okay, so the interesting thing is note that these are even, right? So if we were to trace these over onto the y-axis, we would have f of a equals f of b, right? So f of a equals f of b. They're the same height. That's important. That's an important part of the theorem. And this function is continuous. We'll call this f of x is continuous. Not only is it continuous, but it needs to be differentiable. So no corners, no asymptotes, a very nice and smooth function. So what Rolle's theorem tells us is that there is some c, there exists a c, so we'll do the backwards e for there exists a c, such that the derivative f prime of c equals 0. And notice here we have the horizontal tangent line. So it guarantees us some c in between a and b such that the derivative at that point c equals 0. That is, it has a horizontal tangent line. Note this only works if f of a equals f of b. Let's see if highlighting that works. Okay, so that's the important thing. If we don't have that, we don't get this point 0. And it also only works if it's continuous and differentiable. Let's look at, so not continuous, right? Let's just do an example of that. You might have something like this. I don't know. Here we go. Here's a nice function that is not continuous, a little piecewise function here. Well, you might have your a and your b still, and your f of a equals f of b. A, and here's our b, but notice there's no point in between them. There's no c in between a and b that gives us that 0 derivative because it's not continuous. Same thing with asymptotes, right? You may have a function like this with some asymptotic behavior going on. I don't know, just whatever, pick a random function, and then you could still have your nice a and your b. F of a is still f of b, but there's no point in between a and b that gives us that 0, that derivative of 0. I mentioned that it also has to be differentiable, so let's do a case that's not differentiable. Just imagine a function like so comes up and not differentiable. One good way to not be differentiable is to give it a corner like that. There we go. So now let's take our a and our b again. So we'll do our a here. The b has to match it in terms of height. So those go down to our a and our b. So everything set up is continuous. F of a equals f of b. But note there is no point c, because right at this very corner point, the derivative is not defined. Derivative does not exist there. So we can't say that f prime of c at that corner is 0. It's undefined. And there's no other point where f prime of c would be 0. So it's important to make sure that your function meets those conditions of continuous and differentiable. Let's look at the theorem in more detail. Let f be continuous on the closed interval ab and differentiable on the open interval ab with f of a equals f of b. Then there is at least one point c in the open interval ab such that f prime of c equals 0. So this theorem in words is essentially saying the same thing that we said with the picture. If you want to write this slightly more mathematically, you could write, so there is at least one point, there exists a c in element of AB. Okay, such that, a lot of times that's abbreviated S comma, or S period, T period, S dot T dot, such that. So there exists a c in AB such that f prime of c equals 0. One of the fun aspects of learning new math is getting new symbols to work with. So I enjoy using the there exists an element of symbols. Let's look at the kind of exercise that we would use Rolle's theorem to solve. Use Rolle's theorem to show a point is guaranteed to exist and then find the point. For g of x equals x cubed minus x squared minus 5x minus 3 on negative 1 to 3. Okay, so Rolle's theorem is actually a pure existence theorem, so it says nothing about finding the point at all. So notice that these exercises that say go on and continue and find the point are actually going beyond Rolle's theorem. Rolle's theorem doesn't care one bit about finding the point. All it cares about is the point's existence. So there's a little bit of a confounding thing happening here with this exercise. Okay, so step one, let's use Rolle's theorem to show that a point is guaranteed to exist. Let's check that it meets the conditions to use Rolle's theorem. That is, we have to show it's continuous on that closed interval and differentiable on the open interval, and that the f of a and f of b are equal. Okay, so is it continuous on that closed interval negative 1 to 3? Well, yes, it is. Check, because it's a polynomial, and we know that polynomials are continuous. Okay, next we ask, is it differentiable on the open interval negative 1 to 3? Well, check. Again, because it's a polynomial, the only way that this thing could not be differentiable is if it had a corner or an asymptote. Polynomials have no corners and no asymptotes. They're nice and smooth. So yes, this function is differentiable. So it's important to address both these issues, right? You don't have to say a ton about them. Like we're not going deep in proving that polynomials are continuous right now, or that they're differentiable. We're just addressing the fact that they are. But you want to mention these, or else technically you haven't justified using the theorem. So anytime you do homework with this kind of stuff, or see it on an exam, you want to say, yes, it's continuous, and maybe make a case of why, unless it's pretty obvious. But here I'm just saying, yeah, polynomials are continuous, polynomials are differentiable. So make sure you do that step. Okay, let's check out the endpoints here. F of negative 1. Okay, so I'm getting negative 1 minus 1 plus 5 minus 3. That is 0. All right, and how about f of 3? Okay, so that gives us 27 minus 9 minus 15 minus 3, which is also 0. So great. That's what we needed to have happen. So we have f of negative 1 equals f of 3. So our endpoints are equal. So we've justified the if part of the theorem. Right, so here is the if part. Every theorem will have an if and a then. Okay, so we've justified the if, so then we get the then from the theorem. So here's our then, so what does the theorem give us? There is at least one point, C. Okay, so let's go on here. So then we can say by Rolle's theorem, RT, there exists a C in, okay, you don't have to use the fancy math language, I'm just going to negative 1 to 3, such that, I'll write that part out, f prime of C equals 0. Rolle's theorem has guaranteed us the existence of such a point. Now this is where Rolle's theorem stops. The exercise asks us to find a point, but no, we might not even be able to find such a point. In this case we can, but it's kind of misleading because oftentimes we wouldn't be able to find the point. Okay, so let's go ahead and find that point. Well, we simply take the derivative, g prime of x, and set it equal to 0. So let's see, we have 3x squared minus 2x minus 5, set it equal to 0. Well, now we're just doing good old-fashioned algebra here. We can factor this thing down, 3x and x, and how about 5 and 1, and let's do minus plus. That gives us x equals 5/3 and x equals negative 1. Now negative 1 doesn't cut it because our interval is an open interval here, so we're not including the endpoints here. So negative 1 is actually on the endpoint, so that's out, giving us x equals 5/3.